here we go. So we got the streaming started, and we'll go ahead and start the lecture. All right, are there any questions from last week? Because we missed Monday. No one remembers anything about what we talked about a week ago. Okay, so let me sign in first, and then we'll get back to what we talked about last week. Okay. I did not forget my password. I changed it because I have to change it every 3 months. All right. Okay, so last week we talked about functions. What qualifies a set of two tuples to be a function, because not all sets of two tuples are functions. There's one specific requirement for something to be seen as a function. So there is this one. Let me open this up so that we can kind of just recap what we talked about last time. So in order for something to be a function, we need this whole thing to be true in order for f to be a function. So instead of starting from the beginning, which will take a long time to get back to here, I'm going to start here. Okay? So we'll start with this particular statement and just kind of try to decipher what it means, and then we'll go on from here. So what this statement is saying is for all e that is an element of x. So this is the quantifier. For all is a quantifier, and it binds e as a variable to a particular element of x, which is the domain of f, or the domain of f that is claimed to be a function. We don't know for sure whether it's a function or not. So are there any questions about the notation up to this point for all e in x, okay, which is from here to here? Yep. Mm-hmm.
Why is x relevant?
What is?
Like, x isn't used anywhere else in that statement.
It is used way before. So in order to determine whether we're talking about a function or not, we have this assumption all the way up here. Okay, so this establishes which is the domain. X is the domain, y is the codomain, and f is what we think is a function, but how do we know whether it really is a function or not? Okay, so we know that f has to be a subset of the Cartesian product between the domain and the codomain. Remember last time I changed this from a proper subset of to just subset of. Okay, and getting back to the statement that we have here. So now the next question is, what is this whole thing talking about? Because this has to be true for every element in the domain. Okay, so what are we talking about that has to be true for every single thing in the domain? So we are talking about something, the cardinality equaling to 1, because we see the bar symbol, which is the cardinality of a set, which is the number of elements in the set. That has to be exactly 1, not at least 1 or at the most 1, has to be exactly 1. So what is the set? Now the set that we are talking about would start with a brace and ending with a brace. Okay, that describes all the elements. So in this case, every element in this particular what I would call an ad hoc set, because it doesn't have a particular name, is each element has to be a two tuple, and if it is a two tuple, it naturally has the first component, which we'll call P, and the second component, which we'll call Q. But then we have requirements of these two components. The first requirement, which is the left-hand side of the conjunction, is, okay, let's start with E. What E are we talking about? The same E that is now already bound to an element of the domain because of the quantifier. So the quantifier has already bound E to a particular element in the domain. So the first requirement of an element inside this ad hoc set is the first component of the two tuple of that particular element has to be the same as E. Then we also have a second requirement. We also want PQ. Now whatever Q is fine, okay? But that has to be an element of F as well. So all the two tuples, okay, in short, all the two tuples in this particular set has to start with E, but it can end with whatever, okay? And then that two tuple has to be an element of F, which is a set of two tuples. Are we doing okay so far? So we're constructing a set. Yep.
So the PQ tuple is an element of X cross Y because F is X.
Oh, we are not interested in X cross Y because we're only interested in F because of this requirement.
For P equals E, could you also just say P is an element of X?
No, because it is specifically a particular element in X. So this is binding it. Okay, so if this is confusing, remember I used pseudo C code to explain the same thing? Yes? Okay. In fact, that is also posted on Canvas, so you might want to revisit the C code equivalent of this logic here. Okay? Does it remind you guys of the resource or the topic, the stuff that we talked about last time?
It was still a little confusing.
Huh?
It was still a little confusing. Yeah, the last part.
It is still a little confusing?
Yeah.
Okay, what about, okay, let's take a look at the, where is the, yeah, there we go. Okay, so, okay, this doesn't show very well, does it? Let's download it first. Save my guys. And then open it. No, that doesn't look very good either. All right, fine, we'll use the long way of opening it. That'll be the one. There we go. Does this jog your memory a little bit? Okay. So when you look at this part here, E is bound to one thing in the entire universe. Okay. And then in each iteration of the for loop, it is bound to the post operation of each iteration is to say, okay, now let's look at the next thing in the entire universe. So E is just going through every single thing in the entire universe, okay, sequentially, one by one. Is that okay? And then the first thing we need to do is to look at the other function, which is PEXF. Okay, these are all passed as parameters. And then the first requirement is, okay, if E is not even an element of the domain, forget about it. We are not interested. We don't need to know anything about it. Is that okay? And it is not returning 0, it is returning not 0, which is not false, which is true, because I commented in class that C and C++ has a really peculiar way of looking at true and false. Okay, you know false is 0, but you don't know what true is, because true can be anything other than 0. So that's exactly why I use not 0 to represent true. Because I don't want to use a 1, I don't want to use -1, because those are all implicitly saying, oh, -1 is true, but what about 5? It may be true, it may not be true. But in reality, anything other than 0 is true. So that's why I use that to represent true. Does everybody understand why, if E is not an element of X, I just automatically say, yep, okay, it meets that requirement.
It has to do with implication.
Yep, it has to do with implication. Because, because we are only interested in properties of elements of X. If something is not an element of X, we just say, okay, we are going to ignore you. But if I want to ignore something, I also want to make the statement true because I want that statement to be universally true for all things in the entire universe. Okay. So the else goes back to here, and this is where we do the counting, the cardinality. So when you look at this code here, okay, this code is corresponding to this part. So once we have E already fixed, E is a particular thing, and we know it is an element of X, then we go for the inner loop. Yep.
So the statement isn't saying that all E's exist in X. The statement is saying for all E's that do exist in X.
Yes.
Okay.
So this is, you can look at this for all symbol as for all or for each. Okay, you can say for each or every. So for every e in x, the following has to be true. Okay. So looking at these alternative way of describing the same symbol can be helpful because I know what is for all because I've used it for many years. But if you're new to it, it really helps to say, okay, this is also known as for every, for each. Okay, so you have to go through everything in x and say, okay, do you meet that requirement? Okay, fine. How about you? Do you meet that requirement? You have to ask that question to every single thing in x, and they all have to meet that requirement in order for this entire thing to be true. So are we still doing okay so far with this stuff? Okay? So we have this part here, describing, why it is useful to understand the concept of a function using this particular way to define a function, which is not the same as how your math class or your calculus class will define a function, because those are all continuous function. This is what we call a discrete function. So is that part okay too? Okay, all right. So let me switch back to go back to the modules, and I'm not done with functions yet, so your homework assignment is not quite ready yet, but I will get it ready soon, and I will post a video about it as well. Okay. So the next topic that we're going to talk about will be injection, surjection, and bijection, and I don't think we can get to aleph null today, but this is a really fun topic. When I say it's a really fun topic, many people would usually frown because when you look at this whole thing, okay, let me point to the part where things go a little bit yeah, yep, yep. But the idea is interesting, so I'm just going to skip all the way to the bottom here. It is basically saying the cardinality of all the natural numbers, which is this one here, is actually the same as the cardinality of the Cartesian product of natural numbers. There's a way to map, okay, using a function. There's a way to map every single coordinate in a two-dimensional space where the coordinates have to be natural numbers. There's a way to fold everything into just natural numbers. And it's a one-to-one mapping. Okay, you can give me a coordinate, and I can give you the natural number corresponding to that coordinate. Or you can turn it around and give me a natural number, and I can point out where in the two-dimensional space is the pixel corresponding to that natural number. It's a two-way function. That is pretty cool, don't you think? Nah, you guys don't think that. It's too early to be cool, to have anything that's cool. But if this can fold 2D space into 1D, then we can handle any number of dimensions. So let's say for whatever reason you have to deal with a 6-dimensional space. Fine. Fold it into 5 first. Then fold it into 4, 3, 2, and then eventually down to the set of natural numbers. Okay, so that's kind of where we're heading. Okay, we're not quite there yet. Okay, but when we get to this point, then we can start to look into the math. The detail of the math is kind of ugly. Okay, so there's a lot of derivation, but I try to explain the derivation of the mathematics as well, because I think I'm trying to explain how I reason all of this stuff out, and as a result, some of you may benefit from going like, oh, okay, so this is the line of thinking. This is how we approach the problem. And some of you can just ignore that, okay, because you may not find it useful at all. All right, so we're going back here. This is where we want to end up at, probably by sometime next week. So today we have to go talk about injection, surjection, and bijection, and these are all words describing functions. Okay, so we start with injection. An injection or injective function, also known as an injection. Okay, I used the wrong article. It should be an injection. Injection has each element of the domain mapped to a unique element in the codomain. Okay, so that basically means if I know f is already a function, in other words, the requirement that we were just looking at, which is this one. So if we know that this requirement is met already, f is in fact a function with x as the domain and y as the codomain, this additional requirement will also make f an injection. So let's take a look and see what this really means. Okay, so this is basically saying for each element in the domain, for each element in the domain again, so P, Q are both elements of the domain. P and Q not being the same implies f of P is different from f of Q. That is the definition of injection. Is that okay or not? You cannot map you cannot map two different elements from the domain to the same thing in the codomain. As long as you're not doing that, your function is an injection. Or you can say your function is injective. Yep.
Like your function's linear. Like your function's linear.
A linear function is injective. So if you say, f of x is 4x, it is injective. Because a different x value will map to a different y value or a different value after you apply the function. Yep.
So I guess if we're trying to think of it more like in a math sense, just to get a picture of it, you think of like a parabola on a graph. You have two x points, and they're not going to correspond to the same y point they would correspond.
Right. You can look at it, from a graphical perspective. You can look at it that way too.
Oh.
Yep. Well, okay. So you can have, yeah.
I think I wrote it that wrong, but yeah.
Right. So no two x can map to the same y.
Yeah.
Yep. So the parabola, is not going to work because with the parabola, you would end up with two different x's having exactly the same y. So that would not work.
Okay, so
exponent would work.
Yeah. Cubic, like a linear.
Cubic would work. Yep.
Something like a line also probably.
Absolute number would not work because we're mapping 5 and negative 5 to 5. Yep.
So is injection, is that synonymous with continuous functions?
No. We are in this class. We are not too concerned about the continuous functions. We haven't really gone through the discussion of L0, which is basically defining whether a set is infinitely but countable, infinite but countable sets, and that's the concern of our class. Okay. So, are there any questions about this particular statement? Yes, no, sort of. Okay, so yeah, go ahead.
I don't know how to word it anymore.
Okay, so let's try to look at this code, look at this statement in mathematics symbol, and come up with the C code to do the same thing. Okay, so I think that usually helps a little bit because we are familiar with C code already. Okay. So to look at this one here, injectiveness is to look at it like this. Okay, so we say int is f injective. Okay, so we have a function f known to be a function. We have a set x, which is our domain. We have a set y, which is our codomain. Okay, so these are the input to this particular C function. So what we want to do is we can see that the for all, the p and the q, they are nested. So we're going to set up exactly the same thing in loops. Okay, so we first have to use a particular truth or boolean to remember whether the answer is supposed to be true or not. Okay, so we assume the answer to be true, which is not false. Okay, so unless we find something that makes it false, it is true. So that means if you have an empty set as a function, it is automatically injective. A function that does not do a single thing is injective. Okay, because we assume it to be true, you have to find me a counter example to show that it is wrong. Okay, so we have two loops. Okay, we say for element P equals first element of X, and the loop stays here as long as we have another element. Okay, so
We haven't exhausted X.
Yep, have not exhausted everything in X,
Yeah.
and P gets next element in X. Okay, so this loop is obviously not actual C code, but it resembles C code in the way that we say, okay, initialization is P is the first thing in X, as long as we are looking at something that is actually in X, then do the following. And then after each loop, after each iteration, we say, okay, let's look at the next thing if there is such a thing next thing. Okay. So this is an outer loop, and obviously we have an inner loop. So I'm going to be very lazy here. Just copy and paste, re-indent everything, change P to Q. Because that's exactly what this statement is saying. Okay, for P in X, in parentheses for Q in X. So I'm emulating exactly the same structure in C code. Okay, so what are we asking about here? Well, the first thing is, what if P and Q are the same? Well, according to this part here, if P and Q are the same, we are not concerned, right? Because it's an implication. If P and Q are in fact the same, then P is different from Q is going to be false. But if the first part of an implication is false, the implication itself is true. So technically, we're not concerned about it.
Basically, like we got a P that wasn't actually part of X, or Q wasn't actually part of X, it wouldn't matter.
Say that one more
Same
time.
thing if like for some reason we were checking a P that wasn't in X or Q that wasn't in X, it doesn't matter.
Correct. But in this particular case, we know P and Q are both in X because that's the way we set up the variables. Yep. But one easy way to do this is to spell it out. Okay, is to spell out the implication, and then we just say answer is answer and. In other words, we are just stacking on the previous answer. Okay, so I'm not even going to go for the quick, easy way to exit the loops. Because we want this whole thing to be true for everything in X as Q, everything in X as P, so it's one gigantic conjunction. Okay, so this gigantic conjunction is going to have this one here, and I'm going to use this one here. Okay, if not P not equal to Q. Okay, because X A implies B is not A or B. I'm just using that definition of implication. So I'm using exactly the same thing as we have here, but I put a negation because I'm turning the implication into a disjunction. Is that okay? Okay, so here's an OR. F of P does not equal to F of Q. So this is a literal translation of the logic in mathematical notation. I'm just counting the parentheses. I think that's right. Okay. Yep.
Is that a comparison equal or assignment equal?
That's which one?
The answer equals answer.
That's assignment. So I'm taking the current answer, and then I say, okay, let's make a conjunction out of the current answer with the following. In other words, once answer becomes false, there's no chance of becoming true again, because it is one gigantic conjunction, right? If there's one thing in the conjunction being false, the entire conjunction is false. Okay? And I don't even bother with having answer as a part of the conditions, which will give me a really quick way to get out of the loop. But this expresses the same logic as in the statement. Yep. Go ahead.
You're checking P equals Q. If P equals Q, don't you want it to evaluate false?
Say that one more time.
If P is not equal to Q, then
Uh-huh.
it should be true. But
Okay, so let's check out what happens when P and Q are exactly the same. Okay? If P and Q are exactly the same, what is this? It's false, right? Then what about this?
No, if P and Q are.
Yep, go ahead.
Did you mean to use set y for q? Is it supposed to be? Did you mean to use set y for q or? just
Say that one
x?
more time.
Are we using set y for q?
Set y. Oh, there's no use of y. Well, the only thing that we use, set y is when we apply f. Then this is an element of y. This is also an element of y. So I'm using the regular way of using a function as well, because f of p is the application of function on p. So we get a value that is an element of the codomain, which is y. But this is a literal translation of the mathematical statement. Okay, I just turned the mathematical statement into something that you can evaluate linearly or sequentially, but they mean exactly the same thing. Is this okay or not? Sort of. Okay. This is something that only a programming or computer science professor can do, because your math professor may not know how to code or use pseudocode to explain the same kind of concept. So this is the code corresponding to this particular statement. All right, can we move on? Yep, question?
How come the function when it's different than the PQ?
How come the function?
Yeah, they're both looking at not equal to, but in PQ, it's not.
Okay, so I use not equal to because I want to mirror what I already have in the original mathematical statement. Because I'm expanding the implication to not blah blah or blah blah. That's the definition of the implication. So yes, technically speaking, the negation of P does not equal to Q is really just saying P equals Q. But I do not want to use that because then it doesn't resemble the actual mathematical notation. So are we still doing okay so far? Okay.
Was the answer a bool?
It's an
Answer.
int.
No, answer is an int.
Oh.
I'm using straight C, not C++,
Oh.
nor Java. No fluff.
See, strange. See.
Straight.
Straight. C.
Yep. Basic. Really, elemental C. Yep.
So after the logical and, either one of those statements could be true to return true.
Yes. Or if at least one is true, then it returns true. Because I don't want to use either or because that's exclusive or. Yep. So if at least one of the two statements is true, then the entire disjunction is true.
And when would the function comparison be true?
If you have a function that is not injective, that will meet that requirement. So that's what we are trying to do. Is f injective or not? Yep. So an injective function would never make this part true. But if you have a function that is not injective, then there exist at least two elements of the domain that will map to the same thing in the codomain. That makes a function not injective. So that portion will become false, right? But if this is false, the first part is got to be false too, because this is using short-circuited evaluation. In other words, if P and Q are the same, we don't even bother to apply the function. So by the time we apply the function, we know P and Q are not the same, which means not P does not equal to Q is false too. So then you have false or false, which turns the entire thing into false. And once you have false on one side of conjunction, the entire thing is false. But once answer is false, it can never become true again, which means that function is not injective.
Should you get a statement to break out?
Hmm?
Should you break out? And then
Well, if you want to optimize, you can. Okay, the other way to short circuit it, yeah, you put it in the condition here and not use the break statement. Yeah, break statement is like. Do you guys know what is a break statement, or continue?
It jumps off
Yep.
the loop.
Yep. Continue will go for the next iteration of the loop,
Yeah,
and then break will get out of the loop. I personally do not use either, because they are not very good for the analysis of the algorithms.
Professor Antos would never let us use it in his classes.
That would be correct.
Yeah, it was a big no.
Yeah, because it makes the analysis of the algorithm very difficult because it's not really structured anymore.
Yeah.
You cannot just look at the condition of a loop and know what is the condition of getting out of the loop, because something can break out of the loop and you have no idea what is actually going to be true after the loop itself.
Yeah.
All right. Shall we move on? Okay. So I think I have a few examples here. So assuming f is a function, AB is our domain, 1, 2, 3 is our codomain. This is supposed to be a single arrow, by the way. I used the wrong one. Then this is not even a function. It is not a function because it did not meet the requirement that we started to talk about at the beginning of the class. Because we have two things. A as an element of the domain is now mapped to two things in the codomain. That makes f a non-function. If f is a non-function, I don't even talk about whether it's injective or not, because injectiveness only applies to functions. Okay. This one is a function, but it is not injective. It is a function because A, B are both used up, so everything in X, everything in the domain are mapped. Unfortunately, we don't have A, B mapped to different things in the codomain, which means this particular function f is a function, but it is not injective.
It's surjective, right? It's surjective.
No, it is not surjective.
Oh.
It is not surjective, and it is not injective. We'll talk about surjectiveness later, okay? This one is injective, even though there's one, I'm missing an end curly brace here, but it is injective because the two elements of X from the domain, they're mapped to different values in the codomain. So is the example helping to illustrate what injectiveness is about? Okay, very good. And just like before I forget, I'm gonna go fix it up. This is 290. I'm missing a close curly brace here.
Your single arrow.
And the single arrow. That's just an uppercase versus lowercase. Uppercase is double and then lowercase is single.
Wow.
Yep, so it's a little bit easy to make a mistake. There we go. Date. There we go. Ta-da. All right. So are there any other questions? Yep. Mm-hmm.
Can you say one more time why it would be an injection, the last one?
The last one? You mean this one?
Yeah.
Ooh, I just noticed this is a smaller one. I'm sorry, I got distracted. It is injective because A and B are mapped to different things. No two elements from the domain are mapped to the same thing in the codomain. That is why it is injective. Okay. So now I'm compelled to fix it. Let's see. That's because I put it in the wrong place. It has to be before the backslash close paren because that becomes a part of the equation. There we go.
Yeah, at least you fix it and update it. You know, some professors will let those things go for a couple semesters before they catch it.
Oh, because it's easy for me to update it.
Yeah.
Ta-da! Okay, now it looks good.
That is your story.
Yes.
the two sides of the force is now balanced.
Yep.
Yep. Okay. So that's injectiveness. Okay. Surjectiveness is seeing things from the codomain's perspective. Okay. So a surjective function, also known as a surjection, is a function where every element in the codomain is mapped to. In other words, you're using everything in the codomain. That's the only requirement to be surjective. Is that okay? So in English, it's relatively easy to say, right? Everything in the codomain is mapped to from the domain. So how do we say that using mathematical symbols? Yes, go ahead.
Can you have mapped elements in the codomain that aren't touched by the domain elements and still be surjective?
No. So in a surjection, everything in the codomain has to be mapped to. I'm not. Was that what you asked, or?
Yeah, everything is mapped to each other essentially. Nothing is left.
Nothing is left unmapped. Correct. Yep. Okay, so let's take a look at the mathematical notation of what surjection may look like, which is this statement here. So it says, for each Q, okay, for every Q in the codomain, there has to exist a P in the domain such that Fp equals to Q. That's it. That's one way to look at it. Yep.
So you don't have to use all the domain elements.
Well, but in order for f to be a function, remember this is an additional requirement on top of being a function. So you do have to use up everything in the domain. But if you also meet this extra requirement, then the function is also known as surjective. So we can also call that function a surjection. Yep.
Is it possible to be surjective without being injective?
Yes. Easy example. So that's a good question. We'll go ahead and take a look at a particular example of something like that. Not injective, but surjective. Is that what you were asking for?
Yeah.
Yeah. So we say f is mapping from AB to 1. That is guaranteed to be. So the only function you can make out of this is easy, because you only get one thing in the codomain, right? So the only function you can make out of this one is going to be mapping A to 1, and then mapping B to 1, 2. There are no other ways. Given the constraint of our domain and codomain, there are no other ways to make a function out of this. Because of the requirement that everything in the domain has to be used, can only map to one thing in the codomain. But because it is also automatically surjective, because there's only one thing in the codomain, so everything has to map to it. The only alternative as a function, given this is the codomain and that is the domain, is an empty set. That is also a function, not very useful. So the empty set is one option, and then this is the only other option as a function for f. Yep.
So for a function to be surjective without being injective, the codomain has to have fewer elements than the domain.
Correct. Yeah. So you can use the cardinality. It implies a ordering of the cardinality. Yes. But it's not the other way around.
Right.
The ordering of the cardinality of the domains does not necessarily conclude whether it is surjective or injective. Yeah. Go ahead. Sorry.
They can have the same cardinality though, and we can have an injection and a surjection.
If they have the same, yes, they can be the same. In other words, if I make this a 1, 2, this will not be surjective anymore. So if they have the same,
Goes back to being injective.
if
No, it would be injective and surjective.
what?
If we have A mapping to 1 and B mapping to 2,
Then it would be both.
Both,
Correct. Yep.
yeah.
But he's specifically asking for an example where it is
Oh.
not injective but surjective.
oh.
Yep. All right. Is everything okay so far? Thought of? Okay. Yep.
If we had like 1, 2, 3, would it be surjective still?
If you have 1, 2, 3 like that, it would not be possible to be surjective anymore.
Because 3 is unmapped.
because you have more elements in the codomain than you have elements in the domain. So you are guaranteed to have leftover elements in the codomain unmapped. So this will guarantee it is not surjective. It can be injective, but it is guaranteed not to be surjective. Okay. All right, very good. Those are all very good questions. Anything else? Yep.
Let's back to the module. My question it's about if you could alt tab back to the module real quick. The part that's in parentheses in the first line where it's I'm still a little confused. How do you read that?
It says, for every q in y, there exists a p in x such that f of p equals to q.
Oh, okay. Thank you.
Yep.
So it's saying for all elements of the codomain, there exists a domain element that the function of the domain element that maps to the y.
Maps to the one from the codomain. Right. Which is basically saying in English, it's saying the same thing as everything in the codomain is mapped to. But it is kind of in a more concise and a more precise way because it's mathematical. Now, there are other ways to look at things too. Okay, the same thing here is also can be expressed as this really kind of longer and more convoluted way of expressing the same thing. So the convoluted way of saying this whole thing is to say for each and every element in the codomain Y, the cardinality of this ad hoc set is greater than or equal to 1, at least 1 basically. Okay, but what is this ad hoc set? Now, by the time we get to here, Q is already bound to a particular thing in the codomain. So Q is already fixed. Okay, the only flexibility is with P. Okay, so we're basically saying, give me anything that ends with Q as an element of F, and we'll make a subset out of it. Okay, and then we're asking the question, what is the cardinality of this particular subset? Yep.
If your cardinality is over 1, though, it's not a function.
No, it is still a function because remember, Q is from Y. Multiple things from the domain can map to the same thing in the codomain. Yeah. It's not the other way around. The one, you cannot have one thing in the domain mapped to multiple things in the codomain, but the other way around is okay. So that's why I only put a requirement of greater than or equal to 1. Is that okay so far? Now, I have exactly the same kind of thing in injection, okay, that I forgot to mention, I neglected to mention that, is this, okay? So injection, or a function being injective, would meet that particular requirement. You go like, oh, I think we have seen that before. Well, you have seen something like that before, but not exactly. Because this one is changing the at least 1 to up to 1. That is the only change. So what does it mean? It says for every Q in Y, so everything in the codomain, so Q is already fixed at this point. Pick out all the elements in F that ends with Q as the second element. That set has to have a cardinality of only up to 1. That is injectiveness. Does it make sense to you? Yes?
Can you remind me of the definition of cardinality? Because now I'm just more confused.
It's counting the number of elements. Cardinality is basically length or size of.
Like A comma 1 and B comma 2. Like the number of tuples in a set.
A single 2 tuple is considered a single element.
Okay.
So going back to why we can't have more elements than the function. No.
Domain.
Okay, there are several sets that we are talking about. X is a set, it is the set of the domain, right? Y is a set, it is the set of codomain. F is a set of 2 tuples that defines what maps to what. Yeah, so it is a set of 2 tuples. 2 dash tuple, which means it is a tuple with 2 items in it. Is that okay?
It's so
Yep.
wide.
I still don't get exactly why the cardinality is less than one.
Because if it is more than one, that means you have multiple things from the domain mapping to the same thing in the codomain. That will make it not injective anymore. So everything in, so if you look at things from the codomain perspective, if I'm an element in the codomain, only up to one thing can map to me. There may be nothing mapping to me. Okay? In other words, there may be a lot more elements in the codomain than there are elements in the domain, where you have many elements in the codomain not mapped at all. That's fine. Then this will be 0, right? But at the most, I can only have one thing mapped to me. No more than one. Is that making any sense?
Yeah.
Okay? Yep, go ahead.
So it would become 2 in the case that for a Q that exists in Y, you have more than one P that is a tuple.
Exactly. So if I scroll up just a little bit, one of the examples would have 2 as the cardinality of that set. If you look at this particular example, both A and B are mapping to 1. So when Q is bound to 1, then this particular set would also consist of A1 as well as B1. Because the 1 is already bound, we have fixed, right? So we are asking, okay, what elements in F ends with what tuples? What 2 tuples in F ends with 1? We got 2. A1 and B1 both ends with 1 as a 2 tuple. So now the cardinality of this particular set will be 2, right? 2 is not less than or equal to 1, which means it fails the requirement of being an injection function. It is not injected. Is that okay?
So cardinality of the for cardinality to be 0, it has to be an empty set, and an empty set
No. Well, if you look at this one, because our codomain is 1, 2, 3, right? So when Q is bound to a 2, then the cardinality of this set would be 0, because nothing in F ends with 2 or 3. Is that making any sense? This part says for each and every element Q in Y, I want the following to be true, right? So Q has to bind to 1, has to bind to 2, has to bind to 3 in sequence, right? Because we have to evaluate every single possible element in the codomain. When Q is bound to 1, this is false already. Okay, fine. But what if Q is bound to 2? When Q is bound to 2, because 2 is an element of the codomain, right? Then we're asking, what in F ends with 2 in a 2 tuple? Nothing, right? Then you have an empty set. The cardinality of an empty set is 0. 0 is less than or equal to 1 is true.
So this is another kind similar to the implication, because you have a condition that doesn't match. So that therefore automatically you assume there's.
Well, this one has nothing to do with implication per se. This one is just because I'm looking for less than or equal to. All right, are we doing okay so far? Okay, so with this class, you really kind of have to study the material after a class, because otherwise, you will lose track of that stuff within 15 minutes. Or maybe 3. It's faster than you can cook ramen noodles. As opposed to C and C++, you can probably retain that stuff for an easy 2 or 3 hours. With this class, it's 15 minutes. So it really helps to study or reinforce your understanding by reading the material or just kind of thinking about it a little bit more after the class. Okay, so are we okay so far with injection, which is basically saying no 2 elements from the domain would map to the same thing in the codomain, or in surjection, which is basically saying everything in the codomain are used. So any questions about these 2? Each one on its own, it's kind of useful, but not terribly so. But when they're together, we have bijection, which is really cool. Okay, so bijection is where we want to get to. Okay, Because when we have bijective or bijective functions or bijection, it means we have inverse functions, which is great. Because whatever you do, there's an undo. Okay, we like undos. Yep.
Kind of jumping the gun. The only way to have bijection is if you have the same number of elements in each set.
Yes. Yep. Exactly. That's one of the byproducts of being a bijective function. So bijection is easy. By definition, bijection means it is a injection and it is a surjection. A known to be function. Okay, f has to be a function first. But on top of being a function, we know it is injective and we know it is surjective. If a function meets all of those requirements, then it becomes a bijective function, or it is also known as a bijection. Okay? So we're just doing a conjunction. Cool. So from earlier, this is one way to express injection. Okay, remember up here, this is one way to describe injection. And I'm sorry for scrolling around a lot faster than I really should, but this is the qualification of being surjective, okay? Because we just saw that up here. This is the qualification of being surjective. Do you see how similar they are? The only difference is one is less than or equal to 1, the other one is greater than or equal to 1. You guys notice that? So what if I make a conjunction out of these two? Well, if it has to be less than or equal to 1 and greater than or equal to 1, it equals to 1, right? And you might think, oh, but that is the definition of being a function. No, almost. Because when we define what is a function, we are not looking from the perspective of the codomain. Okay, when we try to describe something as a function, we are looking from the perspective of the domain. This is looking at things from the perspective of the codomain. Okay? But then you might think, but if the cardinality is a 1, who cares whether it is a domain or the codomain? Well, you're absolutely right. And that's the reason why any bijection function or bijective function has an inverse. There's a function to go in the reverse order. Is that making any sense?
It has an inverse or it is its own inverse? It has an inverse or it's its own?
It has a inverse function. It is not necessarily its own inverse function. Okay? So bijection is important because it implies reversibility or inverse a function. So now we take a look at what is an inverse function. A bijection is reversible, which means given a bijection f that maps from the domain x to the codomain y, there's another bijection f inversed that will map from y to x. I'm not going to call y the codomain because it is actually a domain from the perspective of f inversed. Okay, so I will just use x and y in this case and not use domain and codomain. So for each element of x, we can apply, this has to be true because that's the property of an inverse function. Is that okay? And also, because it is they're inverses of each other, this is true too. For each e in y, this has to be true as well. Are we doing okay so far? Okay, it's good. All right. Any questions about this part? Yep.
So if the codomain or the domain, or if the codomain domain of the function do not have the same amount of elements, they cannot be inverse.
It cannot be bijective. Because a bijective function must have the same number of elements in the domain and the codomain.
No, but can they, I was talking about inverse. So
For inverse?
yeah, if they don't have the same amount of elements in the codomain and the domain, can it not have an inverse?
Okay, so let's look at it from the perspective of just f. Okay, so we know that. Okay, let's look at the three cases. So we look at f, which maps from x to y. Okay, so let's look at the case where x is the cardinality of x is greater than the cardinality of y. Okay, what does that imply?
It's not
implies one of the things cannot be possible.
It's not possible.
What is not going to be possible anymore?
Bijection.
Well, bijection is not possible, but bijection is the conjunction of injection and surjection. So if you break it down to injection and surjection, which one is not possible anymore? Injection is not possible anymore because you have more elements from the domain than you have elements in the codomain. So that implies F cannot be injective. It can still be surjective, but injectiveness-wise, it is not possible anymore. If the cardinality of X is less than the cardinality of Y, what is that going to imply? Implies F cannot be surjective because you have more things in the codomain than you have things in the domain, which means there has to be something in Y that is not mapped. That makes it not surjective. Now, is it injective? Yeah, it can still be injective. We don't know for sure. Okay. Is that answering your question? And in order for F to be bijective, it has to be injective and surjective, which means if the cardinality of X and Y are different, F cannot be a bijection. Right? Yep, go ahead.
You cannot have an inverse unless it is bijective.
That is correct. In order for an inverse function to exist, it has to be a bijection. Is it okay so far? Sort of? Okay. Now these are tools that we're going to use to describe many other things that are going to be useful. So by itself, injection, bijection, surjection is slightly useful, okay? But they're not exactly very useful. But they can be very useful when we combine it to describe other things. Okay? So this is a proof. Okay, so let me point out where the proof starts. But can we prove this? In other words, can we prove that every function that is a bijection has an inverse function? Okay, that's what I want to prove. Because hey, if I cannot prove it, then we have a problem. Okay, this class is all about proofs, and rigorous math. So the rest of this part here is basically the proof of if you can show me that F as a function mapping from X to Y is a bijection, I can prove that F inverse has to exist as a function. And it also has to be a bijection. Is that okay? So you can read the rest of this, okay? But the key to this part is really to recognize the symmetry. The symmetry is between this statement and this statement here. You can see how these two are almost exactly the same, except one starts with for all p in X, the other one starts with for all y, for all q in Y. Okay? But otherwise, they are symmetric. So once you know that they are symmetric, then you can come to this conclusion and basically say for each p in X, for each y, for each q in Y, if PQ is in F, then QP has to be in the inverse, and vice versa. Because just because of symmetry, instead of writing P and Q, I can write it backwards, Q and P, but that becomes a new mapping. It becomes a new function. But every time I see a PQ in F, then we can write a QP in F inverse. But when we count how many of those things do we have, they are the same. And when we look at the injectiveness and surjectiveness, it is also the same because we're just flipping the order. So that is the crux of this particular proof, is to basically use the symmetry that is achieved only because F is a function and F is a bijection, in order to basically say that there is an inverse function. Are we still doing okay so far with this? Okay, all right. So we're getting back to the sorting example in module 289. I'm not sure how many of you remember that one. But at the very end of this particular module, we talk about how do we define an algorithm that is actually a sorting algorithm. And one of the things that we want to express is this part here. Okay, so we are basically trying to express, okay, what does it mean when we say that this algorithm is a sorting algorithm and it's doing it correctly? Efficiency is not even important in this case. I'm only concerned about the correctness of the sorting algorithm. Okay? So just to remind you what we have already talked about is this is the input condition. In other words, this describes the array coming into a sorting algorithm. Okay? So A bracket I is your usual notation, which is denoting element I of array A. Okay, so that part is just a syntax thing. K subscript I, on the other hand, is a constant. Okay, we have the same number of constants as there are elements in the array, and these constants do not have to be unique. Okay, I just need a way to remember what A bracket I used to be. Okay, so Ki is the value of A bracket I when I was given the array to sort. Is that okay? So Ki never changes. We don't do anything with Ki in the algorithm itself. We move the values of A bracket I all the time, but we don't change Ki. Ki is fixed. So the question now is, how can we say that a sorting algorithm is doing everything correct? Most people can get this part just fine, okay? Because this means the array, the end result array is sorted. Okay, for every index I that is from 0 all the way to bar A bar minus 2, it is bar A bar minus 2, not minus 1, because we need a comparison to the next element. So that's why we have to stop one element short when we are talking about just the index. Is that making any sense? Okay. So that is just saying that everything in the array is in a particular order. In this case, it's a non-decreasing order. I can make an array in a non-decreasing order pretty quickly. Just assign zeros to everything. Right? Change the entire array to 0. Now it is sorted. Turn in that homework assignment in cisp440 or something and see how many points you're going to get. So obviously we're missing something, right? Because the other requirement of a quote-unquote sorting algorithm is everything that was in the original array has to be in the final array in the same number of frequency. In other words, if you're given 5 ones, 2, 6, and 1, 10, you have to be able to find exactly that number of values in the output array. You cannot just say, oh, we got those 3 values, but in different frequencies. That doesn't work, right? It has to be the same frequency. So the key is now to say that, okay, so we have a way to express that too. So we can say that we also want this to be true. In other words, for every array, for every index in the array, we want the final value of each element to be a constant corresponding to one of the original array elements. But this by itself is not enough either, because f of I may not be injective, right? If I map every single I possible here to a single 0, this will become true, wouldn't it? And all I have to do is to pick the first element of the entire original array, copy that through the entire array, and then I say, oh, I did this requirement already because now we have a function f that maps everything to 0. That doesn't define what a sorting algorithm is supposed to do. So what is missing? What is linking this particular example to what we just talked about today? We need f to be bijective, okay? Because that says, oh, this from the beginning of the entire sorting algorithm maps here. This maps here, this maps here. So everything has a place. Every single initial value has a place in the final array. Then we can say, okay, now it is a sorting algorithm. And on top of that, obviously, the ordering has to be right too. Is that making any sense? So this is one application of why the term bijection is useful, because now we can describe and say that f has to be bijective in order for this to be a sorting algorithm. Is that okay so far? Now, do you guys remember me talking about automated program verification? okay, where we use statements like these to describe the desirable outcome of an algorithm. We give the computer a particular algorithm, like bubble sort or quick sort or whatever, and then the computer will automatically prove that, okay, starting with that as the initial condition, we guarantee that this is the actual end condition, and therefore, whatever algorithm you have me analyzed is a sorting algorithm. It is correct. Do you remember that part? Yes, sort of? Okay, so I had a conversation with a student this morning, and we were talking about AI, artificial intelligence, and you might think automated theorem proving or automated program verification is an application of AI. Yes, it is. But what if we can describe the desirable outcome and actually have the computer to figure out what algorithm will meet that outcome? In other words, we are not asking the computer or the AI to say, oh, double check and make sure that this algorithm meets all of these requirements. We are telling the computer and say, come up with an algorithm that can do this. What do you think?
No. I think it would be so convoluted.
Well, if an AI can play Dota and beat a human player after 3 months of playing against itself and learning everything by itself,
Oh, it's possible.
I think
Yeah,
the
best.
possibility is there. Okay. So just to talk about this other project, if you're interested, let me know and I can sign you up, as a student intern for this project. One of the adjunct chemistry professors here is interested in finding cures for cancer. I mean, a lot of people are. But he is particularly interesting, his project is interesting because he's making it accessible to high school students and college students. So he's running open source molecular modeling software, so he can come up with a 3D model of certain cancer cells and whatnot, pathogens, basically. So once you have the 3D model, then a human can look at the shape of the 3D model and then go like, oh, I think I can design a molecule to fit into this keyhole. And whenever you can find a key to fit into a keyhole, with pathogens, you have found the cure. Okay? So that part is usually done by a person, by a human being, okay, is to figure out what kind of protein or how you fold a particular protein to fit into that keyhole so that you find a cure for that particular disease. But we are now looking into having a computer to find a molecule for us. That's what the student project is about. Okay, so we are looking into Markov process. We're looking into reward function. There's a name for that. Reinforcement. That's it. Reinforcement learning, RL, and a few other things. So I have yet to meet with the chemistry professor, kind of to talk more in detail, because I lack the chemistry domain knowledge to get this to work. Okay, to model. Okay, but how do you fold protein? What are the steps? And how do you distribute the probabilities? But once we have both the chemistry domain knowledge and also the knowledge of AI and how to apply problem-solving techniques in AI, this is we can move forward with this project. Now, are we going to find cures for common cancers? Probably not. Okay, but we'll get the ball rolling. Yep.
We'll finally be able to use all that folding at home data.
Yep. But we are already in that age. As I was commenting this morning when I was talking to another student, we used to think that we are in the information age, right? The internet age, the automation age. We have gone past all of those already. Automation sounds cool, but it's really boring. Because automation means you walk into a GM automotive plant, okay, you get all these gigantic robots, they can put a car back together, using parts with high precision and high repeatability. But nonetheless, it is still the same thing over and over again.
You can design a car.
It cannot design a car, exactly. It will take a design and put it together for you. But everything has to be quote unquote programmed. AI is pushing us to the point where the computers can solve problems. The computer is now adaptive. It can find solutions to problems on the fly without human supervision. And that is that's one gigantic step beyond automation, because you don't know what the computer is going to do. Okay? And I think I talked to you guys about a Space Odyssey, 2001, A Space Odyssey. That was made in 1967, which is old, because that's before I was born, and I'm old. And Arthur C. Clarke already saw that, oh, this may be a possibility. You give a computer with AI conflicting objectives, the computer will try to figure out a way to meet both objectives, but it may not be what you would consider as an acceptable solution. Instead of asking the astronauts first, are you supposed to know about this mission? Oh yeah, we got clearance here. The computer automatically assume no one on this ship is supposed to know about this objective, and since they have displayed knowledge of this mission, I have to finish the mission somehow. Oh wait, I'm a computer. I can finish the mission all by myself. So to keep this mission a secret, I'll just kill the crew. That was the solution. That's the reasoning of the computer. But it was not the fault of the AI. It is the fault of people who input the directives, not talking to each other, and the directives turned out to be conflicting and not really coherent. Isaac Asimov has his own series of books and novels about all of these things. So all the things that you might have heard about, AI safety is one that is really touted these days. And also, by the way, for the first time, Elon Musk and Putin agree on one thing. Do you guys know what they were agreeing on just a few days ago, like yesterday?
Something about AI.
Yeah, AI is going to be the source, the reason why we have the Third World War. Is it going to slow down anything? No. It's going to speed up everything. Because now that we know the other side is going to use AI to help them win the war, we'll step up our own effort. So not only are we going to make it happen, we'll make it happen sooner.
And I must stop all wars by making one more war.
That reminds me of all the Gundam movies. The war, the violence that will end all violence, right?
I was thinking World War II, like the war that end all wars.
Well, that philosophy has been used many, many times. Okay, so we have 5 minutes left. Okay, but I do want to interject, these kind of seemingly unrelated stuff, because it's not enough anymore just to study what you study at school. This is the foundation. Okay, without understanding the math and stuff like this, some of the AI algorithms and some of the new ways of analyzing algorithms and whatnot, you won't be able to understand that either. So this will give you the basic tools to do all that stuff. But for the most part, the moment you walk out of the class, that stuff is outdated already. Well, sometimes, most of the time before you walk into the class, it's already outdated. All right, so we're going to move on to the next one. I'm not going to get into depth, today. We have 5 days before we talk about this again, so please go ahead and study the stuff that we already have online. But Aleph No is basically talking about the cardinality of sets that have an infinite number of elements. So we basically say, this is the definition. Okay, don't ask me why, it is just the definition. The cardinality, when you count the number of elements of the set of natural numbers, it is by definition known as Aleph No, or Aleph 0. Okay, just a symbol. Okay, but the point is, we can make other sets equivalent, having a cardinality that is equivalent. So now I try to compare the cardinality of the set of all integers as opposed to the cardinality of the set of all natural numbers. And you might think, oh, one only grows in one direction, the other one grows in both directions. So one is going to be bigger than the other one. Well, that turns out not to be true. Okay? As it turns out, there's a way to map. Okay? There's a function f to map the set of all integers to the set of all natural numbers. But not only do we find a way to map it, we also find out that this particular mapping is bijective. What does that mean? That means if you give me any integer, I will find the natural number corresponding to it. If you find me any natural number, I can tell you what integer maps to that natural number. Well, since it's a one-to-one mapping, it is bijective. Now I can say, well, if I call the cardinality of all natural numbers aleph 0 or aleph null, I can also describe the cardinality of the set of integers exactly the same way. Because for each element in Z, there's one in N, and vice versa. So the bijective function is now used to establish equivalency of cardinality. And not just any cardinality, it is cardinality of a set that has an infinite number of elements. Okay? So that's the significance of this particular topic. And the rest, there's a lot of derivations here, which is kind of, it takes time to read it, okay? But I do encourage you guys to spend the time to read it so that you understand the rationality and also the tricks, the methods to derive equations and proofs. Yep. Mm-hmm.
How do I read that again? I forgot how to read that. I never used that way of writing it then.
It's a ternary operator.
Yeah.
So it's this is a condition.
Okay.
If this condition is true, you evaluate the second part, and the second part becomes the value of the entire expression. Okay. If the condition is false, then you evaluate the third part, and the value of the third part becomes the value of the entire expression.
Okay.
So if you have questions about the question mark and the colon, I strongly recommend you to read about the ternary operator in C, C++, Java, PHP, Python, and so on, because it is used, it's implemented in most programming languages. So it's a very useful, it's a very useful notation.
The Gaddis book they use for 360 and 400 from most of the professors, they have a section on that.
Yep.
The starting out with C++ book use.
Yeah, it's a very useful thing. It's just that most classes